Maddie Simpson with Simpson Math. In this video, we're going to solve exponential equations. So what makes an exponential equation an exponential equation? When the variable I'm solving for is in the place of the exponent. So for instance, if I have 3 to the x is equal to 81. Notice the variable I'm solving for is in that place of the exponent. To help us with this, we're going to use this rule that when we have the base is raised to an exponent, and you have the same base being raised to an exponent, we know those two exponents have to be equal to one another. So we're going to use that here. 3 to the x is equal to 81. Well, let's see if we can make their bases the same. Can I rewrite 81 with a base of 3? Well, 3 times 3 is 9, times 3 is 27, times 3 is 81. So 3 to the 4th power is equal to 81. I can rewrite that 81 as 3 to the 4th power. So now I have 3 to the x is equal to 3 to the 4th. When their bases are the same, then their exponents must be the same. This x must equal to 4. We have solved that exponential equation. Here's another example of an exponential equation. I have 3 raised to the 2x plus 1. Again, notice that my variable that I'm solving for is in that exponential position. This time it equals 27. My first strategy, the first thing I'm going to look for is to see, can I set my bases equal? Can I rewrite this 27 with a base of 3? Well, 3 times 3 is 9, times 3 is 27. So 27 is the same as 3 to the 3rd power. I'm going to rewrite that as 3 to the 3rd power. 3 to the 2x plus 1 equals 3 cubed. Now that my bases are the same, my exponents must be the same. So I can set those exponents equal to one another. 2x plus 1 is equal to 3. And now I can solve for x. Subtract 1 from both sides, and we get 2x is equal to 2. Divide both sides by 2, and we see that x is just equal to 1. Now, I love solving equations because I can always take my my solution, and plug it back in, substitute it back in to make sure that my answer is correct. So let's do that. Take 1, substitute it back in. 2 times 1 is 2, plus 1 makes 3. 3 to the 3rd power is 27. Yay! Here's another example. We have 4 to the x power equals 32. Again, notice that my variable that I'm solving for is in that exponential position. That's what makes this an exponential equation. Now, what I'm going to do is try first to rewrite those with the same base. So let's see if we can write 32 with a base of 4. 4 times 4 is 16, times 4 is 64. Oh no, it didn't work with a base of 4, but maybe there's another base that I can write both of them with. For instance, this 4 could be rewritten as 2 squared. So 2 squared to the x, well, that 32 could be written as 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. 2 to the 5th power gives me 32. So I could rewrite that as 2 to the 5th power. Now their bases are the same, so then I know their exponents are the same. Just as a reminder, when I have a base with a power and it's being raised to another power, we multiply those exponents. So this is the same as 2 to the 2x is equal to 2 to the 5th. Now that my bases are the same, I can set the exponents equal to one another. So I have 2x equals 5, solve, and I get x. Divide both sides by 2, and I get x equals 5 halves. Again, I love to be able to solve because then I can substitute it back in to check myself. Remember, this is the root, so that part is the square root of 4 to the 5th power. Well, the square root of 4 is 2, and 2 to the 5th power really is that 32. So my solution makes sense. Let's try another one. Here I have 5 to the 2 minus x is equal to 1 over 125. So again, my variable is in that exponential position. My first strategy is always look to see, can I set their bases the same? Well, 125 can be rewritten with 5 as a base, but how do we get down to 125? Remember that when I have a negative exponent, it reciprocates my base. So I know that because my 125 is in the denominator, I'm going to end up with a negative exponent there. Then 5 times 5 is 25, times another 5 is 125. So 5 to the 3rd power gives me 125. 5 to the negative 3 is equal to 1 over 125. Once I have their bases set equal to one another, I can then set their exponents equal to each other. Now I can solve. Subtract 2 from both sides so that I have negative x equals a negative 5. Divide by negative 1 and x equals 5. Again, I put that 5 back in. 2 minus 5 gives me a negative 3, which we just saw was equal to 1 over 125. Here I have 7 to the x minus 2 over 6 is equal to the square root of 7. I want to first try to make my bases be the same. Well, I see a 7 on both of those, so I bet I can make 7 be the base. So 7 raised to the x minus 2 over 6 is equal to 7. Remember that square root, like we said earlier, when I have a square root, it's equal to the denominator of the fraction, fractional exponent is equal to that root. So in this case, it's 1/2. I'm raising it to the 1st power and taking the square root of it. Once I have their bases equal to one another, then I can set the exponents equal to one another and solve. Now, when we solve these, there's a couple of different ways to do it. Perhaps you get a common denominator, make this 3/6, and then set their numerators equal. Or you can multiply both sides by the least common denominator. In this case, 6 is their least common denominator. Multiply both sides by 6, that becomes 1. And half of 6 is 3. Then I can add 2 to both sides so that x equals 5. If I plug 5 back in, or substitute 5 back in, 5 minus 2 is 3. 3 divided by 6 is 1/2, which gives me that square root. So when we are solving exponential equations, your first strategy to look for is, can we set their bases equal to one another? Once we have their bases equal to one another, then our exponents are equal to one another and we can solve. In our next video, we're going to look at a method to use when we cannot set our bases equal to one another. Math Made Simple at Simpson Math. Thanks for watching.